Today's lesson is over section 3.8, which will talk about the rates of change in the natural and social sciences. We would like to start with kind of a warm-up, looking at this graph of two different functions, and we'll talk about the derivatives for those functions at particular points. So for the first one, letter A, it's asking for the derivative at 4.5, which means the slope at 4.5. So then that means I'm just looking at the slope, so I'll look at the line for that, so I can actually take the endpoints of that line and find the slope, which gives me the value of 3. At letter B, looking at the slope at 3 for the function of g. Now here, this is actually at a point, so the slope makes that point makes a sharp corner on the graph, so that means it's indifferentiable at that point. Letter C, we're looking at the multiplication of two things and their derivative at a certain value. So this would suggest that I need to use the product rule at 1. So that means f prime of 1 times g of 1 plus g prime of 1 times f of 1. And so then at those points, I'll look at the slope at 1 for f times what the y value at 1 for g is, plus the slope of g at 1, and then the value of 1, or f at 1, which gets me the value 0. I'll do the same thing for the quotient rule at 9 for f of g, or f divided by g. And so I'm really just using the quotient rule to write this all out. And then looking at the graph for 9, I'm able to kind of do the same thing. Kind of reference what the slope is at f and g at 9, what those actual values are at g and f, and then divide them by g of 9 squared. Now, if you're trying to keep up with this, always kind of go back, rewind, look at the graph, and kind of figure out how we get those values. Here I have an example problem where I'm looking at the particle moves along a line and its position in meters at time t seconds is given by the following function. So I would like to be able to find where a particle is at time 0 and time 1. So that means I'm looking at the position, so I'm looking at the first function. So basically I just need to plug in 0 into my original function and plug in 1. So when I plug in 0, I get the value of 31. When I plug in 1, I get the value of 97. Now for the next part, I'm looking at what is the velocity of the particle at t equals 1 and t equals 2, and that is talking about the slope of the particle's path. So I need the first derivative to be able to kind of describe this. So I'm going to take the first derivative of my position function, which is my velocity function, which will be 12t squared minus 90t plus 108. And then from there, I'll plug in 1 and I'll plug in 2. So at 1, my velocity is 30 meters per second. At 2, my velocity would be negative 24 meters per second. Now, the third question is asking when is the particle at rest? That means when the slope or the velocity is at 0. So that means I'm going to take my first derivative and set it equal to 0 and try to solve. Now, I can take out a 6 out of both sides to make my quadratic a little easier to factor. But then once I get that, I can find that it's going to be 2t minus 3 times 2, or t minus 6. So setting those both equal to 0 and solving gives me 3/2 and 6. Now I'm going to use those values for the next piece because here it's saying when is the particle moving in a positive direction. So those are kind of like breaking points, 3/2 and 6, and at 0 when we're starting. So we want to pick values in between those intervals to see if we're moving in a positive direction at those points or we're moving in a negative direction. Now we've already did some of this work by plugging in 1 into the first derivative and 2 in the first derivative from our example in letter B. So I already know that 1 is at 30, so that means it's moving in a positive direction between 0 and 3/2. When I plugged in 2, we got negative 24. That means it's moving in a negative direction between 3/2 and 6. So now I need an extra 1 to the right of 6 to see what it's doing. So I plug in 7, and that gives me the value of 66. And so my interval of when it's a positive direction would be between 0 and 3/2 and 6 to infinity. Now I'd like to find the total distance traveled in the time interval from 0 to 7. So that's going back to looking at position. Now I know the critical points of when we change direction, which is at 0, 3/2, and 6. 7 will also be a critical point because that's when we're ending our interval. Now we already did some work in letter A by plugging in 0 to find that it was 31. So we already know that value, but now I have to plug in 3/2 to figure out what my position is when my velocity is 0. That gives me a value of 105.25. I also need to know when I change back to going positive at 6, so that position value is -77. And then in my ending one, when I plug in 7 or stop my interval, I need to figure out when that, like my last position before it's over, that gives me -46. So now using these 4 values, I can find the distance between them. So I need to find the distance from 3/2 to 0 in that time frame, from 6 to 3/2, and from 7 to 6. And so subtracting those position values will give me their distance in meters. Now notice I'm using the absolute value there because distance is always positive. And I'm always taking the later time minus the earlier time, or the smaller time. So I get those following 3 values, and then I just add them all up. And that gives me a total distance of 211.25. Okay, letter F is asking for the acceleration of the particle at 3. So that means we're talking about the second derivative. So looking at my first derivative, I take the second derivative, I get 24t minus 90. Then I just need to plug in 3 at t, and that gives me 72 minus 90, which is -18. So that is my acceleration in meters per second squared. And then for the last one, I'm looking at when is the particle speeding up. Now the idea of speeding up means that your velocity and acceleration are doing the same thing, so they have the same sign. So when they're both positive, it's speeding up or going faster in a positive direction. When they're both negative, that means they're speeding up in a negative direction. So for slowing down, that means the velocity and acceleration have opposite signs, so they're doing the opposite thing. So then that means they're tapering off and heading towards a velocity of 0. So if I want to find when my particle is speeding up, I first need to take my acceleration function, figure out when it changes from being accelerating faster to slower. So I need to figure out when it's equal to 0 as well. So dividing both sides by 24 gets me the value of 3.75. So that is a critical point. So now I want to figure out what happens in between. Well, I already found 3 to be 1, so I know that that's negative. Now I just need to pick one on the other side of 3, or 3.75, which would be 4, and that's 6. So that means it's positive. So now using the kind of position kind of number line I used for letter D and lining that up in the same kind of format as I've done for the acceleration one, I can see that when I have the same signs would be from 3/2 to 3.75. And so that area, and after 6 on to infinity, they are both positive as well. So that would be my interval for when they are speeding up.